spring 1939 settled uneasily over Aberdeen Proving Ground in Maryland, where American tanks crept along at barely 12 miles per hour, no faster than a man jogging, their engines groaning under loads they had never truly been designed to bear, while across the Atlantic German Panzers ripped through Poland at more than twice that speed, driven by purpose-built engines refined over years of focused development. And this stark contrast weighed heavily on Colonel William Christie as he studied. Intelligence photographs scattered across his desk, images that told an unforgiving story. The United States possessed barely 400 tanks, while Germany was producing more than that every single month, and the clock was already ticking toward a war everyone knew was coming, leaving America perhaps 18 months to bridge a technological and industrial gap that Germany had spent a decade perfecting. And it was in this atmosphere of urgency and looming inadequacy that Christie's eye drifted one afternoon to an overlooked object in the corner of his office, a technical manual for the Wright R-975 Whirlwind, a 9-cylinder radial aircraft engine producing 400 horsepower, already being manufactured in large numbers, an engine his engineers dismissed as irrelevant to armored warfare because aircraft engines ran at high revolutions with propeller cooling in thin, high-altitude air, while tanks crawled through dust, mud, and heat with almost no airflow at all. Vibrations alone threatening to shake a vehicle apart, textbooks insisting such a conversion was impossible. Yet Christie saw what others did not, recognizing that while German engineers had labored for years to design the perfect tank engine, American industry had unintentionally built something remarkably close and simply called it an airplane motor. And the real question was not whether it could work, but whether anyone had the courage to try, a question Christie answered himself when he pushed through the heavy oak doors of Continental Motors headquarters on a gray October morning in 1939. Carrying a leather briefcase filled with what amounted to America's most pressing military secret, including intelligence photos from Poland showing German armored columns moving at speeds no American tank could match and production estimates that suggested the United States would be helpless within 18 months if nothing changed, and as he spread the photographs across the polished table in a conference room heavy with the smell of machine oil and cigarette smoke, Detroit's finest automotive engineers leaned forward with professional curiosity until Christie delivered his blunt message that thousands of tank engines were needed immediately, faster than any conventional development program could hope to deliver. Then he opened a second folder and presented the specifications for the Wright R-975, an engine weighing around 1,300 pounds yet producing 400 horsepower, already rolling off production lines less than 20 miles away, prompting Chief Engineer Robert McNamara to study the drawings with skepticism born of years designing automotive power plants. Knowing the engine ran at 2,400 revolutions per minute, created massive gyroscopic forces, depended on airflow that tanks simply did not have, and generated vibrations that would destroy transmissions and crack hulls, objections Christie had anticipated, countering them with German intelligence showing that German tank engines averaged only about 150 hours between major overhauls, required specialized lubricants, precision parts, factory-trained mechanics, and 3 to 4 years of development time the United States simply did not possess. And as the room fell silent, McNamara gazed out over the factory floor where assembly lines hummed, Henry Ford's production philosophy suddenly suggesting a different way forward, and he turned back with a realization that shifted the entire conversation, proposing that instead of asking whether an aircraft engine could power a tank, they should ask whether an aircraft engine could be modified to solve tank problems, a question that launched weeks of intense engineering analysis as Continental's team dissected every aspect of the R-975, discovering that its radial layout actually offered superior cooling potential, that larger fins and forced airflow could replace high-speed wind, that reinforced mounts and rubber isolation could tame gyroscopic forces, and by November 1939 they had drawn up plans for a modified engine featuring a massive cooling fan, custom mounts, altered fuel and electrical systems, while still delivering far more power than any American tank engine in existence. And when the first prototype arrived at Aberdeen on a cold December morning, installed in an experimental M2 medium tank with a redesigned hull to accommodate its wide diameter, Test engineer Captain James Mitchell climbed aboard with deep skepticism born of years dealing with unreliable engines, only to find the radial rumble to life smoothly, powerfully, and then continue running for 6 hours without failure as he pushed the tank through mud, sand, and steep grades, temperatures holding steady, vibrations absorbed, fuel consumption improving, and by January 1940 the results were undeniable. The adapted aircraft engine outperformed every existing American tank engine in power, reliability, and efficiency, raising not doubts but a new challenge of how to produce such engines in unprecedented numbers as war clouds gathered, a challenge that transformed Continental Motors in spring 1940 into something closer to a wartime laboratory than an automotive factory, with engineers and machinists working 16-hour shifts to solve problems that seemed insurmountable, starting with cooling, addressed by a crankshaft-driven fan and carefully designed shrouds that cost horsepower but delivered consistent thermal control, then vibration, solved through elaborate mounting systems developed alongside Chrysler's tank teams, which revealed unexpected benefits of the radial layout in evenly distributing stress and heat, while maintenance challenges forced redesigns that allowed crews to service engines in muddy fields under fire, not heated hangars, and by June 1940 durability testing showed steady power, improved fuel economy, and reliability that surpassed traditional designs, just as France fell and production demands exploded, pushing Continental to rebuild its manufacturing processes entirely, install new assembly lines, train workers in radial engine assembly, enforce rigorous quality control with dozens of inspections per engine, and by September 1940 produce more than 800 engines per month, a feat that soon found validation in British reports from North Africa where Sherman tanks powered by these engines maintained operational rates far exceeding German Panzers, and after Pearl Harbor the transformation accelerated as the M4 Sherman's design perfectly accommodated the radial engine, aligning with an American philosophy that favored reliability, speed of production, and logistical simplicity over technical perfection, enabling Continental to scale output to levels German planners could scarcely comprehend, producing thousands of engines per month at lower cost, while maintaining strict testing regimes, and combat soon confirmed the wisdom of this approach at El Alamein and across North Africa, where Sherman formation sustained long advances with minimal breakdowns while German units lost significant strength to mechanical failures, a pattern repeated in Tunisia, Sicily, and Italy, where American crews developed confidence in engines that ran for hundreds of miles and hours without failure, even as production feedback loops drove continual improvements, increasing torque, efficiency, and service life, until mid-1943 Continental was producing more tank engines monthly than Germany produced complete tanks, though rapid expansion brought challenges of inconsistent supplier quality and dust infiltration that caused premature failures. Problems identified through systematic analysis and solved through the development of improved variants with better filtration, stronger components, and stricter supplier controls, validated by brutal testing that simulated desert storms, Arctic cold, and combat shock, and these improvements proved decisive in Italy where American armor advanced with unprecedented operational rates, revealing a stark contrast between German reliance on specialized maintenance and American emphasis on field serviceability, a contrast that grew even sharper as production totals climbed toward 50,000 engines by the end of 1943, shifting the strategic balance irreversibly, and by the time Allied forces landed in Normandy in June 1944 with thousands of Shermans, many powered by engines originally designed for small aircraft, the gamble had become a cornerstone of Allied strength, because while German Panthers and Tigers boasted superior armor and firepower, their engines demanded resources, lubricants, parts, and maintenance infrastructures the Reich could no longer supply under relentless bombing, whereas the R-975 ran on standard fuel, used interchangeable parts, and could be repaired quickly under combat conditions, resulting in stark differences in operational availability as German units often fielded only a fraction of their nominal strength while Sherman units maintained high readiness, enabling sustained advances that overwhelmed German defenses. A reality that became brutally clear in the battles of France, where German tanks frequently broke down during maneuvers while Shermans maintained mobility, allowing American commanders to exploit tactical flexibility, culminating in Patton's rapid advances where continuous operation over long hours shattered German defensive planning, and by late 1944, even German intelligence acknowledged that American armor seemed almost immune to mechanical limitation, an impression rooted not in superior metallurgy or precision engineering, but in an industrial philosophy that valued robustness, adaptability, and mass production, and by war's end Continental's transformation stood as one of the most extraordinary achievements of the conflict, proving that a nation willing to rethink assumptions and leverage its industrial strengths could turn an aircraft engine meant to carry mail and crop dusters into a decisive instrument of mechanized warfare, reshaping the outcome of battles and ultimately the war itself.